gotta unmute before I start talking. Hey there, folks. Hope you're all doing well out there. I'm back here with another video looking at application of derivatives and focusing in on the topic of functional analysis and using calculus in the process of analyzing functional behavior. And we've been talking intervals of increasing and decreasing, and we're going to continue with that concept of intervals of behavior, and we're going to look at this time around intervals of concavity and look at inflection points, finding the points. We've discussed those where we change concavity in a graph going from concave down to concave up, right? Finding those inflection points and then using those to help us define these intervals of concavity in our functions. And this is where we are focusing our attention in this set of notes, folks. Inflection points and intervals of concavity. And as I open here with, again, this is very similar to what we have seen for intervals of increasing and decreasing behavior. Right? Except it's an analysis that we perform on y equals f of x, some function that involves the function's second derivative. It's been a little while since we've talked second derivatives. Well, we did a little bit in linear motion when we were talking acceleration. But again, here we come back and use second derivatives again with our functional analysis. That second derivative tells us information about concavity in our graph. And you might ask, how does second derivative describe concavity? And what it is describing, folks, is the slope, the behavior for the slope of the tangent line for the two different cases of concavity. Or maybe what I should say is, you're just describing the slope of the tangent line's rate of change or behavior changing with respect to x. What you will notice is when you're looking at something that is concave down, the slope of the line tangent to the curve will behave in a very specific manner. It will go from being positive to 0 to being negative in value, which highlights that it is, if it's going from positive to 0 to negative, it's decreasing in value. And similarly, for a region where we're concave up, the slope is going to be going from negative to 0 to positive in value, which is, if you're going from negative to 0 to positive, you are going to be increasing in value. So what we're looking at when we're looking at concavity is the increasing and decreasing behavior in our slopes. And where do we analyze for increasing and decreasing behavior is with the derivative. And where are we going to find our slopes is with the first derivative of f. So we're going to end up having to take the derivative for the first derivative of f, which is the second derivative. That is why this analysis happens with respect to the second derivative. And this is what you see developed here in my notes. All right. Here we can see f is concave down in this illustration. And what this illustration is illustrating that is, if we are concave down on this interval, right, the slopes of the lines tangent to my curve start off here positive. We can see they are increasing, right? So we are positive. We then hit a point right at the peak, at the apex, at the top of the graph, which the vertex, which we might call the maximum value, right? Where it's going to be equal to 0, where we have that critical behavior in our graph. And then on the other side of that critical behavior over here, after 0, we're going to be negative. So on a graph where we're concave down, on a region of a graph where we're concave down, as this illustration illustrates, the slopes of the lines tangent to the curve will start off with positive values, becoming 0 and then becoming negative in value as we move through positive values of x, or careful there, as we increase through values of x. As we increase through values of x, the slopes will go from positive to 0 to negative in value. Right? When we are concave down. Similarly, as x increases through that concavity, if it's the case where we're concave up, as this illustration illustrates, right? The slopes of the lines tangent to our curve will start off being negative, will become 0 at the vertex, again down at that valley, right, at that base or that bottom, right, of our curve, where our critical point equals 0, right? And then it'll turn positive in value on the right half of the graph, where we are concave up. We'll go from negative slopes to 0 slope to positive slopes, indicating we are, if we're going from negative to 0 to positive, we are increasing in value. The slopes will be increasing in value as x increases through this concavity. In the case for concave down, as x increases through this concavity, the slopes will decrease. They'll go from positive to 0 to negative. When we are concave up, they will increase, going from negative to 0 to positive in value. So this is why in an analysis of concavity, we look at the second derivative. Right? The second derivative is going to be part of that analysis, right? So that's why I say here in general, to examine where y prime is increasing and decreasing, an analysis of f double prime is performed. An analysis of its derivative is performed. The derivative of y prime, f prime of x. Right? And again, because a function's derivative describes its intervals of increasing and decreasing behavior, and we want to describe that for f slopes given by y prime or f prime of x. Right? If we bring this into a definition, we see here by definition, right? As we've noted, inflection points are going to be the locations between these intervals of concavity, right? And where we're concave up or down, we will see the slope of the line tangent to the curve increasing or decreasing in value with an analysis of the second derivative, right? What we say here is for the function y equals f of x, the intervals of x where f is concave down occur over values of x where the second derivative of our function f double prime of x is equal to the value of 0. Right? Otherwise, right, the intervals where f can be found to be concave up, right, occur over values of x where f double prime of x is going to be greater than 0. Right? Concave down indicating a decreasing behavior, so your expected derivative would be less than 0 for the slope of the tangent line. And in the case where you're concave up, you would expect your slope of your tangent line to go from negative to 0 to positive, increasing in value where your derivative describing the slope would be, well, your interval of decreasing behavior would happen where your derivative is greater than 0, derivative of the slope's derivative, right? F double prime of x. In terms of inflection points, those occur, right, where f double prime of x is either equal to 0 or, like the case for critical points, also perhaps does not exist. Right? And now that I think about it, I might actually include an example of that here at the end of this notes. maybe I'll go do that right now. Let me throw that example in here. Just to highlight, because certainly it's good to see these different cases for concavity. And I'm thinking of an example particularly. So let me pause the video here real quick and we'll go in and add that example. And I'll be right back, folks. All right, I'm back here. I think I got it all worked out. And gave us a second example, so that's great. So let's look at these cases, a couple of cases here for concavity. The first case is polynomial functions. We see concavity in polynomial functions. Right, for any degree greater than, what would that be? A degree greater than 1, right? Second degree and beyond, quadratics and beyond. Don't sneeze. So here, consider this third degree polynomial. 4/3 x cubed plus 2/3, plus 23 halves x squared minus 6x plus 5. Right? If we look at the first and second derivatives of this function, this should be quick derivatives. Fundamental rules will get us to our derivatives. First derivative would be simply 4x squared plus 23x minus 6. And our second derivative would be 8x plus 23. We would get a nice linear function to describe our second derivative, where we understand now that our inflection points are going to occur where that second derivative either equals 0 or does not exist. Well, that second derivative is linear. It exists everywhere. The only concern we're with is with where it equals 0. And if we set this equal to 0 and we solve for x, we should see that that would equal negative 23/8. And negative 23/8 is going to become a location for our critical for our inflection point. It can be seen f double prime exists everywhere, and again, x equal to negative 23/8 is going to be our inflection point. Right? Is where it equals 0. Right? So an inflection point in the graph occurs at that value of what we would say is negative 23/8, comma, negative 625/16. So an inflection point in the graph of f occurs at the, let me say it this way, location of x equal to negative 23/8. And we'll say here corresponding to the coordinate. Let's point out this is a coordinate, not an interval here, folks. Where I'm taking negative 23/8 and substituting it back into the function to actually find the coordinate of inflection. This would be at the coordinate negative 23/8, comma, negative 625/16. As for an interval of concavity, though, that negative 23/8 is going to play a role there, right? What we will notice is that 8x plus 23 is actually greater than 0, right? When x is bigger than negative 23/8. If we think about that graph has a y-intercept of 23 and a slope of 8. So it's going up. So at negative 23/8, we're going to be bigger than that value. The output is when we're to the right of that x value, greater than it, right? At negative x being greater than negative 23/8. And it's going to be less than that when we're to the left of it because of the slope of that second derivative, that linear function. The linear function is going to be increasing, right? So we must be greater than it, 0, when we're greater than that value because we were equal to 0 at that value. And we must be less than 0, less than this value because we were equal to 0 when we were at that value. And the case that we have an increasing behavior, strictly increasing. right? And we see that, I believe, here in our graph. And here I didn't graph it. Ooh, I should probably sketch out the graph for this real quick. And let me go do that. I just realized I don't have that graph, and I would like to support that with a graph. So let me do that real quick here, folks. We fade back over. All right, folks. Luckily, I'm good at whipping up graphs pretty quickly on Mathematica. So here's a graph of this polynomial function here, folks. And we can see that negative 23/8, that's a little less than negative 3, which is where we're at on our graph right here. That's a little less than negative 3. Let me highlight here, right? A little less than negative 3 down here in our graph, right, is where we would expect x to equal this negative 23/8. And notice the graph from negative infinity all the way up to negative, that location, negative 23/8, the graph is concave down. Right? The slopes are going from positive to 0 to negative. They are decreasing in value. That's describing by this behavior before that point being less than 0. If we were actually to graph this line, it would cross through the x-axis right at that location, and it would be down here less than 0. Right? It's 0 at this location, and then it turns positive to the right of that location. So from that location to the right towards positive infinity, this graph is concave up. And that is what we see happening in this graph. This being what we call the inflection point in the graph. It's where the graph changes its concavity from concave down to opening up in its concavity. And that's all illustrated here in this graph. All right? So I did want to give you that illustration to go along with that. All right? Nothing's worse than not seeing the picture at hand. And here's our picture of this polynomial. And its concavity intervals, right, with its inflection point. Now, I did say I wanted to include one other example. In this case, I wanted to look at when do we encounter inflection, and I should be careful with this, locations of inflection, right? We do call them in general inflection points, but they can be and that's why I changed the notes above into just a location of inflection, because what we see here in this next example, I'm looking at the function 1 over x. Where if we look at the first and second derivatives, we get negative 1 over x squared and 2 over x cubed for the first and second derivatives, respectively. And we notice both of these do not exist at the value of 0. They also never equal 0. But specifically, if we're interested in their critical points and potential critical or inflection locations, right? Locations of inflection, we're interested in where the second derivative either equals 0 or does not exist, and it also does not exist at the value of 0, right? So x equal to 0 becomes a location of inflection, and it should be at least a critical location, because in the domain of our function, if we go back and note, it's actually not in our domain either. The domain of our function is actually from negative infinity to 0 and from 0 to infinity. And at that point, we do have a critical location because it is an inflection location. Where if we go down and we look at the graph, or if we just take note to begin with the second derivative here, it is less than 0 for values less than 0, and it is greater than 0 for values greater than 0. That x cubed will shift between negative or positive in value, whether or not x is less than or greater than 0 in value. And thus it will decrease before 0, and if it's decreasing before 0, it's concave down, and it will increase after 0, and if it's increasing after 0, it's concave up. Right? And that's what we see happening in our graph here. Before 0, when we go from negative infinity towards 0 in this graph is concave down. It's curving downward. It's concave down. We're going from a slope that's really close to 0, not exactly 0, but really close to 0, but heading more and more towards negative infinity. So it's actually decreasing in that behavior. Going from 0, very close to 0, to really close to negative infinity is decreasing. So here we see concave down. On the other side of that inflection location, we do see the graph starts really close to negative infinity and then gets really close to 0 as x goes from 0 to positive infinity. So over this interval from 0 to positive infinity, we must be concave up. And that's what the graph is highlighting. This is concave up behavior. And at x equal to 0, we have an inflection location. It is a boundary between our interval of concave up and concave down behavior. And it does correspond to our domain in this situation. All right? So that was the second case I was considering there, folks, that I wanted to take a look at, where the second derivatives wouldn't be a case where it necessarily equals 0, but would be a case where it does not exist. And we see that here in this case. And it kind of makes me want to change my notes a little bit up here. Let's say here the location in the graph where f changes concavity is known as an, let's say here, a inflection location / point. It's going to be one or the other. And inflection locations / points occur in the domain of f where f double prime of x equals 0 or f double prime of x does not exist. Let's say it that way. And let's bring the idea that what we're looking at here is an inflection location or a inflection point in our graph. And I think that will work for us. All right. Inflection behavior is a little bit more specific than critical behavior, is what I might get into there, folks. Inflection behavior describes behavior between intervals of increasing and decreasing behavior, whereas critical behavior could describe a few things. It could be describing extreme values. It could be describing asymptotic behavior, vertical asymptotic behavior. It could be describing critical point behavior, or sorry, inflection point behavior. Well, so it's not so specific, I'll say. So I want to change this up a little bit here when talking about this. And critical points even is really not necessarily a point, right? Because like I said, it could be a location where we see a vertical asymptote. So it's more of a point along an x-axis. And we could say the same thing here for inflection. So that makes me want to change it back. But I'll leave it as is, folks. I'll leave it as an inflection location or point. And maybe I should go back to the critical notes and change that to critical location or point. And maybe that's what you'll see happen. Yeah. Maybe that's what you'll see happen. All right. And take note of that in retrospect here. So with that all said, folks, I will stop here and I will see you in the next video.